Look how thick it is. When I bought it the same day I got the message. I said, it's important to have that book. At this point in time, I don't have the problem. I want to have it in my library. As soon as I have the problem, I want to look it up. I know these are important problems to be solved when you have these problems. And a few weeks later, a second book came out, this one. And I started reading it, and it's a wonderful book. But don't expect you can read it fast. At least I can't. It takes a while because it has exercises in it, which are not easy to solve, and I only browsed over them. So after I did read the first 2 or 3 chapters, I bought 3 more copies and gave it to my people to read it. Some of them started reading it, and the other one will be forced to read it. So I really enjoyed it. I can recommend to you to buy this book. But now I'm curious, why didn't you speak about this book? Why did you speak about that one? And go ahead. Okay, have fun.
Why did I speak about this one? I think it's a good question.
So maybe next year.
I think it's difficult because at first sight it may seem like it's just a bunch of small details, and that's why perhaps in a small amount of time it's difficult to convey how they play together and what a huge difference they make. Certainly for me, it took me, and I'm not saying I'm clever, so it's probably my fault, but it took me many years to really comprehend and get in my head why they were so important. And because most of these details were given to me by means of mentoring, I thought, well, other people aren't going to be so lucky, so I wrote a book. And the hashing thing, well, as to it being thick, originally it was supposed to be 50 pages, so there you go. So the first thing I want to show is, I'm sure you've seen it before, but it's this invitation to the conference that we're going to be having in Argentina in November. You're more than welcome to attend. And any questions that you have, you may send to smalltalks2008@gmail.com. And you have this flyer in your code, so I won't go into that any further. But I want to show it at least. So now, oh dear. And yeah, I can't get this hand out of the way. So every so often, you see my lovely animated cursors too. So I should do this in the corner somewhere so you can see it. So, what is this all about? Well, this is about essentially a summary of some of the most important things that are useful to keep in mind with hashing. And as such, well, we'll go through this table of contents or slide, whatever. Regarding what's hashing, what are the most common ways in which it is used, why all these why are hash functions so important to consider, and also, well, what the hash function is good or bad. So first of all, what is hashing? So hashing is basically a way to store any arbitrary data you want into something that looks like an array. And with some pieces of data, this is easy to do. You have things like integers, as well as. But we hardly do that because Smalltalk, this is a high-level language. So we have complex objects, and usually it's not immediately clear that they have a natural order to the naturals, 1, 2, 3, 4, whatever. And so what hashing does for us is it allows us to store these objects into something that looks more like an array, only with other benefits that we're going to take a look at. So here we have some real-life examples of how that is done. So for example, a particular bit of hash or for an address could be the zip code, and you can see how this works because an address you couldn't possibly say, oh, my address is 17 million. That doesn't help me a whole lot. And as you can see the address, and the same that happens in the dictionary, the first letter is used as a quick index to find things. And these are ways to do hashing. Now the thing with hashing, however, is that regardless of the amount of data you have O of 1 access, O of 1 deletion, O of 1 addition, O of 1 inclusion check, O of 1 duplicate detection, so it's really quick. And particularly these days where our data sets are becoming huge and more bigger and bigger and bigger, O of 1 built into the hash. And if we compare what hashing is doing with computers to the dictionary approach, in the dictionary, you open a letter tab, and basically you can just do a scan and use some kind of binary search or whatever. But with hashing, it is essentially as having a dictionary that has one tab per word. So you look up the tab, you open, that's it. No more searching. Right, so how does it work? Well, in a simple way, it could be seen as, well, okay, so I create this storage that is going to be the nice looking kind, the array kind. But then you get a function that gives you indices to store stuff in it. And then you just use it to index the array. So for example, if you wanted to store that star, but you can barely see that. Well, maybe you should have chosen another color, but whatever. In there, if you're storing a star in this hash collection, what you're doing is you're saying, well, if the hash of this star is 5, then I'm going to store it at 5. So that's basically how it works. Well, there's more interesting questions. Well, why does it work? Well, because the rule of hashing is that, I'm sure you've heard this many times, but in perhaps in different shape. The thing is, well, if two things are equal, they must have the same hash value. And why is that? Well, because let's say that I have another star, and I want now to know, well, do I have a star in my collection, yes or no? If the two are equal, and they have the same hash value, then I go to 5 again, and I will see, oh yeah, here I have an object that is equal, I have it already. But if things that were equal gave me different hash values, then I'm going to go look at for the star at 7, I'm not going to find it, and I will say, oh, I don't have it. So that's why, in general, the more small-talky interpretation of this is whenever you refine equals, you must refine hash. That's where it comes from. Well, yeah, that's not so easy. So, what problems do we have here? Well, first of all, the hash function, if it's too big, it doesn't, really play well with this array approach, because we're not going to be, allocating 32 bits worth of an array just to store 3 things. So what is usually done in this case is to take the hash function mod, the size of the table plus 1. That's why in find element or nil, or find key or nil, and those methods you're going to see that that's what's going on, at least in VisualWorks. No, sorry, that's implementation of Valloud for some reason. And the other thing is, well, but what happens then? I mean, so the basic property of hashing said if the objects are equal, then the hash value should be equal. That doesn't say anything of what happens when the objects are different. And when they are different and they have the same hash value, then let's call a collision, because the hash values collide. And that causes problems, because now, well, if a slot is busy, how do I store another thing that is different again in it? That's fixed by something called open addressing with linear programming. It sounds very complicated. Actually, it's not. Open addressing just means use an array like we've been discussing. And linear probing means essentially, well, if it's free, if the slot is free, use it. If it's busy, just increment the index by 1 and use that. As you can see, this causes a chain of things that are equal and have the same hash value to start accumulating like this. And that makes deletion more difficult, but we're not going to go into that. But if you check the code for deletion, you're going to see that it's a little bit more complicated, but it works. Well, right. If there's too many collisions, however, this becomes linear search. And this is really bad. And this is why all this stressing to well. Why having good hash functions? Because we want to preserve, or it would be nice to preserve, the O of 1 behavior characteristics of hashes opposed to linear search. So how do we deal with collisions? Well, first of all, they are more than likely you cannot get rid of them. You have them because either you have way many more objects than possible hash values, or because when you look at the hash values about something, you cause collisions. Because, for instance, if the table size is, let's say, 10, well, 10, 110, 2010, and all those collide on 10, and it's a problem. So, if you really cannot get rid of the collisions, then what's usually done is that, the hash collection structure is changed a little bit. But if it's cheap to eliminate the collisions via improving the hash function, then it's much better to do that and keep the hash collection structure simple. But let's take a quick look. So what kind of structural changes could we make? Well, instead of incrementing by 1, we could increment the complicated because all these lovely conditions are appearing like that. And then there's actually something called quadratic probing, and then there's some other issues because of this kind of stuff. Yeah, sometimes it's better to go another route. So, for example, if we had our original array up there, storing actual objects, we could do is store linked list nodes instead. And so when we store collisions, we at least know what the collisions are, where they are, and we no longer have to do linear search. Well, that's very nice. However, the slots are still busy. So if now I try to store something else, it makes it collide, and there's more problems, and so on. So the first thing that one says is, oh, well, the problem is that the linked list is in the hash collection. And let's just pick it out. So we can do that and have the linked list, just hanging from the hash collection. And that's very nice, but now we need to deal with nodes and things like object and next and messing with pointers and so on. And that can take time, so if we wanted to really go fast at the expense of some memory, we put all those things in an array, and that becomes a hash bucket. And this is what I'm sure Martin is very familiar with. So that's for the structure part of it. Now, for the collision reduction part, there's two things that are extremely important. The choice of the size of the array storage, and the quality of the hash function. Again, for choosing the right size of the table, all these conditions appear. This for justification. They are fixed now in VisualWorks, I swear. You should definitely not, stay away from Robertson 2. Definitely don't even think about using Robertson 2 for a mod because those can cause tons of problems. And then we go to the thing of hash quality function. Some people argue that, well, cryptographic hash functions don't have collisions because they've been designed to do this, not have collisions, or to be extremely hard to find collisions. But the problem is that they are very expensive. So if I have like 10 things, hashing with a cryptographic hash, well, that's kind of overkill because I could have done linear search. That would have been even faster. And the other thing is that some other people suggest, well, what you should do, this is one of two approaches, but they are kind of equivalent. What one could do is just consider all the information that has to be hashed, put all the bytes one after the other, treat that as a number, and do, mod the prime, and that's your hash value. Well, that's great, but it introduces the possibility of having to do an arbitrarily long division. It's costly. There's a ton of workarounds for this, and what these are usually called are hash functions. However, it's not so simple, because precisely because they are workarounds, they need tests, and that's usually something that is not done. So let's see, so if we were to go and check out, well, is a hash function good or bad, what are we going to measure? The first thing is that collisions are bad. The more collisions, the more likely that it is that we'll run into linear search and then we'll use hashing to begin with. So what that means up there, it may look cryptic, sorry, but what it means is if we have a data set D, this thing, full of objects that we want to hash, then a hash function f, what this is down here is the set of all hash values. This is up here, this is the set of all objects that were hashed. The vertical bars means the size of the set. So essentially this is measuring the ratio of objects to hash values. And ideally this should be 1, because there should be 1 hash value per object. When that happens, there's no collisions, and there's no collisions that realize happen. So because of that, the minimum value for this score, which is called the collision rate, is 1. Good hash functions usually score less than that. And that may seem very strict. However, good hash functions actually do that. And we think, okay, fine, so we just check collisions and we're done. But it's not so easy. Here's an example where one can see that collision rate is not enough. Because consider, for instance, the case in which we have all the integers between 0 and 1 million minus 1. And our hash function for that is, oops, yeah. Well, okay. And the hash function is take that number and choose the maximum between that number and 1,000. And the collision rate for this hash function is about this. So we think, oh, everything's fine. Okay. So we start storing stuff, and here's our table, size 1 million, because of course we don't bother anything else. And what happens, some people may because laughter. What happens is that then you start storing things between 0 and 1,000, and then they all collide, and they all push everything over to the right, and then you have linear search again. So measuring the collision rate is not enough. Okay, let us try something more complicated. So linear penalty is not enough. Let's try quadratic. I'm sorry. Really not, I'm sorry. So what's that? The thing is, with the collision rate, one collision is penalized with a score of 1, basically. And 2 collisions are penalized with a score of 2, and 3 collisions with 3, and 1,000 collisions with 1,000. But in reality, it would be much better to go quadratic. So 1 collision is penalized with 1, 2 with 4, 3 with 9, and 4 with 16, and so on, because then the higher the spike of collisions, the worse the score becomes, and it becomes worse quicker and quicker, which is the good thing. So what that formula says is that for all the values in the set of hash values, this phi measures is the set of things that cause that value to happen. So it's all the objects that cause that hash value. Look at as consider that as a set. Figure the size, subtract 1, which is our ideal value, and square the difference. So essentially, if we get something here that had 5 collisions, then that's 4 squared, a penalty of 16. That's great, and there's something missing. Consider, for example, that we're running tests, and we have a data set that is really big, and a data set that is really small. For the really small data set, this score may give, I don't know, 2, and you may seem, okay, maybe not so good. But if we have a data set of 1 million things, we get a score of 2, that's really good, because that means there were really, really few collisions. And just looking at that is not enough to tell one from the other. So what we can do is divide by the number of objects we hash, and that's our next check. I don't know how to pronounce, so G-square test. And the good score for this is 0. Good, you say. So finally we have a proper test. Maybe not. Consider again all these numbers from 0 to 1 million essentially, and this hash function here. So as you can see, all the hash values are different. And the chi-square value is 0. So it seems like, oh, okay, this is really good. But if we use the wrong table size, every single object wants to go to the first slot. So everything is a collision, so it's all linear search again. So this test is not enough, because it can let these cases skip through. So the real test is to do this, model basically a lot of primes that actually appear as hash collection table size, and these p-values here are the ones we choose wisely before, according to the conditions that we saw before in the book of Nuth and all that other stuff. So what is a good score here? The more room we give to the hash collection, so that how sometimes you do, oh yeah, I know I'm going to make a dictionary that's really big, so I'm going to resize it in advance. I want to be a dictionary new 1,000, because you're going to put like 500 things in. So basically, what's going on is that the more room you give to the hash collections, the better they should behave, because you're giving them more room. And so what one would expect is that as the value of p increases, then the test of this decreases. If it doesn't, then there's a problem, because I'm giving room to the collection and I'm not getting any benefit. And this is more or less a bound of representative value. And please remember that as soon as one does mod p, there's no collisions just by accident. Now, this of course is way more than your regular workspace test. So for that, there's a tool. Here's it. As you can see, we have a bunch of data sets here, so different things you can hash. There's a drop down here for all the hash functions that are in this image that are compatible with that data set that is selected. You can do a number of actions that we're going to take a look at in a bit. Over here you can see the result, the number of objects, the number of relations, the quality, blah, 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 all this stuff. And the test for the different prime values. So I'm just going to run through a few examples first, so you can get a feel of what's going on. Something that a lot of people hash, let me switch views here. This one just groups the data sets by class, so it's easier to find them. So let's see. Here I have a dictionary of Italian words, the words in Italian. So for hashing words in Italian, perfect thing, just hash them up. So which hash function should we choose? Well, if we take a look at some books, we can find that certain Björn Strustrup has provided hash functions. Two. Let's see. Well, not very good. So we have this here should have been 1.01 or less and far away. This should have been 0, very far away. And what's even worse is that, look at this chi-square values. They hardly ever decrease. They are more or less constant. What's going on? I just, basically I just overshot the size of the collection by more than a factor of 4, and I didn't get any benefit. So I'm still getting collisions. This is the case in which you make a hash collection bigger and it's still slow. What's going on? Yeah. And what are the collisions? Well, here are some of them. So all those words hashed to 10,001, so on and so on. Some of them are funny. Okay, so this is not very good. So we can try it out. So let's see what VisualWorks does today. And it's fine, well, first of all, this is going slower first because I got this jet, which should have, and it shouldn't have. And the other thing is, the tool has more work to do because there's more data to analyze, so the better it is, the slower it goes. You see, counterintuitive, but so we have a grand total of 6 collisions. This is what a hash function should do. This is how good hash functions behave. Anything different, anything that looks different, bad thing. And also, look at these values. The further down you go, the better they become. So that means that with this hash function, if you give it more room to work, the faster it goes. I'm sure that at this point, some people have perhaps an itch to hash something of their own. So what do you suggest we should hash next?
About the words from one of your books.
I had to make that up, so let's try something else.
Do the Dutch words.
Dutch words, sure, why not? Now this is going off, so which hash function? Actually, you know what? Holger Klein-Sorgen added this fantastic thing where you can select all the hash functions and just run them all at once. It may take quite a bit of time, but let's pick a few. Let's see. Which ones do you want? Well, how about this one? What is it? This is the K and R hash function. This that. We could go with this guy as well.
The FNV have.
FNV?
FNV.
Sure. Which variety?
Not the 0.
1A?
1 or 1A, doesn't matter.
1. Okay, so let's try that.
And the hash one from VisualWorks.
Yeah. Why not? Anybody else? Any other takers? Well, you know what? You know what we could do? Look at what I have here. I have a little secret. Where is it? Where is it? Oh, what is it called? I forget. Ah, yes. What was in VisualWorks before?
Yes.
Run them all. It may take a while. There's much more Dutch words than I had Italian words. There's a few more. So this may take a while. And also, these functions are written very naively. So there's a lot of, Viran to 16R, 8Fs, and so on. But eventually it should finish. Hopefully. There's the first one. Okay, quite decent. Very nice, very nice. Only 2 collisions. Very good.
Are you also measuring the time somewhere?
You can actually profile the hash function.
But it's not in the table.
No. Actually, measuring the time the hash function runs is kind of difficult because in this native implementation, the hash function can generate a lot of garbage. Essentially, you end up measuring scalars and that kind of stuff. So, okay, pretty decent.
What do you mean before?
Huh?
What do you mean? When did you fix the hashes?
76.
Uh,
So what's an E?
How hard is it would it be for somebody using VisualWorks to plug in one of these hash things if they think fits closer to the type of data that they're using?
Oh, we can do that in just a moment. Actually, that's great. Can somebody think of an example? No? Well, that's VisualWorks. Okay. Reasonable. And what wasn't there before,
Oh.
not so reasonable. Okay, so that's a good question. So how do we make a new hash function? So, new hash functions, there's this is a plain 7.6 image with the stuff I use for the book, so these are all the experiments I did myself. But there's this package here, and there's, well, a whole bunch. These come with the tools, so you can actually play a little bit and see how they are done. So let's see. I don't know. I could put it whatever. Let's make a new package. Just because we can. So, oops. Right? Right. No class definition. Okay. So this. Yeah, actually. So what do you guys want to hash? Let's pick an example. Anything. Whatever. Strings. Okay. So in order to do that, there's basically a few methods that one has to implement here. One is hash off an object. So an object, we get a string here, so we can do whatever we want. The other one is this. I think that's it. And we just say, sorry. Yeah. Good. So how do you want to hash a string? How about sum all the characters and do something like that? Sum all the characters. So something like that. Now we can come here, we can get a refresh. If you look at the list, we should have our hash function here. There we go. Run it. Not something you might want to do.
But how would you have one of the classes use the same hash function?
Oh, okay. So something that comes up sometimes is that you already have a hash collection and you want to see, well, is it hashing good or not? So something that I added to this tool, let me get rid of that, is this. So for example, let's say, why not? Let's say that we want to see how this guy is doing his hash work. Now we can adopt this into the hash tool. So now we have that representing a data set being all the keys of in small. Now we can say, well, we can hash this with, we can try the default hash. see what happens. Okay. Alright. More or less. Okay. Actually, this is doing identity hash, so these are identity hash values. And we can also make up stuff, you know, like byte string or instances, select any such any not empty, like that. Put this in set. Oops. We put this in set. And we have to do the tool again. So now we have this. And once we do, we can just, I don't know, hash it with something else. 25. Why not? Great. As expected, no collisions. Yes.
What he wants you to do is to swap out the current mechanism that VisualWorks is working with the one that you just created.
You really want me to do that? Now,
Like I say,
okay, hold on.
he's smarter than you are, and so he developed another hash, and he's going to put it in there and try to see what VisualWorks
You don't have to demo it. It
If
just
I
tells how
had,
it's done.
you know, if I had my Cincom laptop here, this is my personal laptop. If I had it, I would. It's great,
Okay,
it's
don't-
great brain surgery. It's really
Don't
good.
do it, just show him how.
Okay, so what one could do to do that,
Yeah, I noticed that.
it's great brain surgery. At one point, you said
Right.
all symbol hashes messed up and all that. It's great.
We're going to move him to sales because he studiously ignored the question really
Thanks.
well. We noticed.
Yeah, so let's see. So what one could do is this. And actually, this is what I did to change it over. So here, yeah, whatever. This implementation actually never works because, or actually never runs because there's primitives behind for byte symbol and all that. There's primitives. So actually, if we look at this, you can see them. So there's like that. Well, this actually resorts to something else. So the implementation for that is this. So that's a primitive. And that's a primitive. Oh, that's identity hash. That's hash. Symbol hash is a primitive. All right, so identity hash. And so on. So, but you can see this range of primitives here. Those are the hashing primitives. So what I will do today to change it, first disable all the primitives. So have them just say super. Then once there's only one implementation to change this one, come here and do it like this. So first, do something like, I had this utility to rehash everything upon first invocation only. So something like that. Actually read like that. Followed by, by that. And what this does is that the first time it's invoked with this particular argument, it causes a rehash of everything. And that's going to send hash again. But the next time, it won't go into this, and so it won't rehash everything, and then we'll let everything rehash with the new hash. And at that point, this implementation is active. When that is done, then you come over, take it out and save the message again. And then everything's okay. One thing, however, is that you cannot use a hash collection to do that. Because it's probably broken. So actually this thing just accumulated these symbols in an ordered collection, so you can do includes and actually do linear search and not resort to hash, which will probably be broken. And that's how all the others got changed.
So Andres, if you're not actually, the person changing the global hash in VisualWorks, but you just want the hash to be different for like your own little collection for some purpose, to not use the same hash for strings that all the other normal collections use, that's a little easier, right?
It's easier. There's two ways to it. And actually, this brings up an interesting topic. In general, when you cannot make any assumption as to what you are hashing, such as, for example, for implementing string hash, basically you're forced to hash everything. Because if you don't, and if you do, the hash of the string is in the first character and the middle character, and blah, 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 then things like URLs all hash to the same. File names all hash to the same. And that's a problem. The issue there is not that somebody is hashing file names and that's not what the hash function was designed to do. The problem is that an assumption was made about the usage of a hash function in the absence of evidence, basically. So in general, hash functions have to hash everything. Because of that, there's basically two ways around the situation you described. One way would be to subclass whatever basic object you have into something of yours and implement hash, and just create those. And the other one would be to do something like subclass set. And set, the good thing about set is that it's nicely refactored, and basically the only place you have to change is this. That you make a subclass, you refine this message, you change that to whatever you want, and you're done. And also, if you want to do identity-based comparisons or identity hash, you also need to change that thing. But that's it. So you put it two places in one.
You could subclass set, change, rather than call hash, call whatever your hash method
Right.
is, and then you have to implement another version of it.
Right, and then you implement the alternative hash, just that hash or whatever it is. No. No.
It's your laptop.
Right, it's my laptop. Hey, leave it alone. So, this is the work, and this is how all this work are done. And there's one perhaps concern. Is that, all this is great, but at the end of the day, what's the consequence for my application? Well, I can tell you an actual story about this. One day, it was kind of late, after 6, 7 p.m., came a user from sitting over there, came over and said, hey, this report that we have to run every day, and it takes half an hour, it's not doing anything, basically, nothing more financial, none of that. It's just trying to write this file from the results that we already have, and it's taking half an hour. Because of that, we cannot leave. We've been working here since 7 a.m., we're tired, we want to sleep, so do something about it. Okay. And I put that in the provider, and about 90% of the work was in, well, remember that method that I just showed you, find element or nil? Well, for dictionary, there's one is called find key or nil. And essentially all the time was spent there because it was doing a lot of linear search. So there were all these points that were in a square. The square went from -20 at -20 to 2020. All the points were inside, and also the points had a characteristic in that xy was equal to xy, or we have xy equal to yx. And because of that, you cannot use which instance variable comes first in the hash, because the hash has to commute. So for example, the hash of 1, 2 has to be the same as the hash of 2, 1. And because of that, the hash needs to commute. And because of that, the hash function that they used was essentially x plus y. It's here somewhere. So let's see what happens. Yeah, well, that's not gonna work. So, okay, but why is that? I mean, why are these numbers so horrible? Now we can tell, well, right, the sum of all these things has to be the same. So each of those, let's go to the positive ones. So for instance, all these points hash to 0. So anytime, or let's say hash to 1, right? So all those points want to go to the first slot in the hash collection. Because they can't, because it's busy, all of that accumulates to the right, and now you have linear search all over the place. So of course it was so. Okay. So I started, playing with this, trying to make something more complicated. And I came with something that, although I didn't have this tool, I could tell you the provider was way faster overall. Even though the hash function itself was slower, way slower. It's because instead of just doing x plus y, it was doing all times and halves and less than greater than blah blah blah, sum more, multiply more, etc. It was way, way slower. And I don't exactly remember which one it was, because I did a whole bunch of experiments after the fact. I think it's this one. Yeah, it's this one. And as you can see, it's way better. It's still bad. It's way better. Way better because instead of chi-squared being 25, it's 3, and you have an order more of magnitude hash values, etc. I ran this with a profiler, and hash was gone from the profiler. I couldn't see it anymore. So I thought, well, why bother? This is good enough, that's it. So instead of half an hour, this thing ran in 90 seconds. And the user just got half an hour more sleep every day. I have to say I had a great experience at that place. It's fantastic. Please keep in touch with your customers. It's great. When you can actually hear what's going on, even if it's bad, it's just fantastic. That's completely invaluable. I mean, invaluable is whatever. You cannot value how much it is because it's too much. Blah blah blah. So really, I mean, fantastic, great. It's great. And well, then I continued making experiments later on because I thought, well, what I did was good, and I ran it, and surprise, it's bad. So I kept running experiments, and finally, I got to this one, and this actually is a perfect result because the comparison of points being that x, y can be equal to x, y, and yx. There is some natural collisions in this data set. That actually produces the perfect result. And you can actually see it because then you inspect what the collisions are, and you see the collisions that you expect. xy equal to xy and yx. So you can see it, you can check, do whatever you want.
Can you share with us the hash function?
Yes. For that particular case, this is what I have done at that place. And you can see it's way more complicated than x plus 1, but it commutes. I still have some collisions, and so on. Are you done? Can I change over to the last one? Yes? Okay, I'll wait. Just let me know. And this is the other one. As you can see, this times 2 plus 1 converts everything into non-zero integers first. And then there's the combination of this and actually all of this mess. So all up to here is one commutative hash function, and this is the other commutative hash function. And because they have collisions in different places, then as a whole they don't collide. And I didn't care for overflow because it couldn't. Yes?
Have you thought at all about collections, so heterogeneous collections of objects where you've got multiple hash functions in the same collection?
No, I'm not. I don't know, I would see that as I mean, at least at first sight, I would consider that as one of the black hash examples. So essentially implement black hash for all the heterogeneous objects, and then subclass set or dictionary to have send that and use polymorphism. Well, at least polymorphism is going to be faster than if true false. Any other questions? No?
One question, where do we get the tool?
Here. In the public story.